Welcome to this lecture series in group theory. In this lecture, we'll be looking at the notion of orbits and the orbit stabilizer theorem, along with a very interesting application. So let us recall a few things that we have seen so far and that we need for this lecture. So recall this notation. This is the group of all the invertible n cross n matrices over Fp. Well, let me just write it for an arbitrary field. So F be some field. Then this notation is for the set of all the invertible n cross n matrices over F. We also use this to denote the set of all the invertible linear endomorphisms from Fn to Fn, and we saw that the two groups are isomorphic in a very obvious way. So both those definitions are fine, but for this lecture, we'll think of it as the set of matrices rather than endomorphisms. Okay, we have seen set theoretic quotienting. Let me recall. So suppose we have a map from a set X to a set Y. Then we have a relation tilde on X defined as X, give me a moment, X tilde X prime if they have the same image. And this is an equivalence relation. The equivalence classes are the set of all the non-empty fibers, which is denoted by X mod tilde. So this is the set of all the non-empty fibers of F, and we saw that we get a natural map F bar such that this diagram commutes, and F bar is obviously injective. What is the map F bar? F takes X to, it takes X to Fx, and this goes to the fiber in which X lies, and this goes to, again, F of X. So that is how this diagram behaves. And this is called set theoretic quotienting. Okay. And then we saw the notion of group actions. So we saw two perspectives. The first one was we have a group G and we have a set X. An action of G on X is a homomorphism from G to the permutation group on X. Alternatively, an action can also be defined as a map from G cross X to X, which satisfies two properties. The first property is that E dot X equals X for all X, where E dot X is shorthand for phi E comma X, and G1 dot G2 dot X is G1 G2 dot X for all G1 and G2 in the group and X in the set. Where again, let me expand the left hand side. It is phi G1 comma phi G2X, and the right hand side is phi G1 G2X. So given a particular action, it is notationally useful to write it, suppress this notation and just write things like this. So these two perspectives we saw, and one can pass from one to the other in an obvious way. So we did that. We saw a bunch of examples. We will see many examples in the course of the next many lectures of group actions. And with that, now let us proceed. Here is a problem that I'm going to use. So let me mark it as star. What does it say? We have a particular kind of n cross n matrix over a field F, where the first column is 0, except for possibly for the first entry. So we want to show that it is invertible if and only if the following happens, meaning this lower n minus 1 cross n minus 1 part is invertible and this is non-zero. This is not a hard exercise, and I will use it. All right. So we discussed the very important notion of an orbit. Suppose we have an action of G on X. So this means that G acts on X, which means that there is a particular, either you think of it as a given homomorphism, or you think of as a map from G cross X to X, which is given. So when we write that, we just mean that such data is given to us and all those notations are suppressed. So suppose G acts on X and little x is an element of the set X. Then we define the orbit of X is defined as, first of all, it is written as this OX, and the definition is G dot X, G in the group G. So that's the definition, but what is going on? We have some set X, and G is acting on it. Little x is a member of this set X. So what we are doing is you hit it by elements of the group. So you hit it by G, you get another point. This point is G dot X. You hit it by some other group element. Let me make it bigger. You can hit it by some other group element, maybe H. So you get H dot X. Right, so this way, basically you take the point X and hit it with every group element, and that is the orbit of X. That is kind of the trajectory of the element X, if you will. So that's the picture. The formal definition is this. And let us take an example. So we have this action of Sn on the first 10 integers. What is the orbit of, let's say, a given letter I? So recall, what is this action? This is the most simplest action. It is, so you take, basically the map is Sn cross the first 10 integers to the first 10 integers. It takes sigma comma j to sigma of j. So that is our action. And what is the orbit of I? If you think about the orbit of I, it is nothing but the entire set X. So this is our set X. This is X, and that is the group. And the orbit of any letter is the entire set X. This is clear because you can always choose a permutation which takes a given letter to a given letter. In fact, you can just take the transposition. Suppose you want to send little I to j, just take this transposition given by this cycle notation. It takes I to j. So the orbit of this is obviously everything. Wonderful. Note that, suppose we have an element in the set X, then there is a natural action of the group on the orbit. So given an action on a big set X, we can restrict the action to the orbit. More explicitly, we are given a map. This was given to us. We can define, maybe I'll write phi tilde. How do we define it? We take G, comma, let me write it as Y, to capital phi G, comma, Y. Now, this phi is this same phi, and this is well defined because this guy is lying in the orbit of X. Why? Because if little y is in the orbit of X, this is also in the orbit of X. I need to justify that. So if little y is in the orbit of X, if little y is in the orbit of X means little y equals H dot X for some H in G, and G dot Y would then be G dot H dot X, which is GH dot X. So G dot Y, which is really that guy, is an element in the orbit of X, because this is of course in the orbit of X. So you pick anything in the orbit of X and hit it by a group element, you get again something in the orbit of X, and that is why this action restricts to another action. The two properties which confirm that phi tilde is indeed an action obviously hold, because they hold in the bigger setting. So that's that. And this is an important remark, that if you have a action on a set X, then you can always restrict the action to any orbit. You fix an orbit and you get a restricted action. So in some sense, this is another example of an abstract group action. All right. Now we can capture the notion of orbits via an equivalence relation. So again, suppose we are given an action of a group G on a set X, then we define a relation tilde on X as follows. So we write X tilde X prime if there exists some group element such that X prime, or let me just write X equals G dot X prime. So that is our relation, obviously. This is an equivalence relation. So I think that is the lemma, yeah. Okay, no, that is not the lemma. So that is a remark that tilde is an equivalence relation. This is a remark or a fact. Let me write this as a fact. Tilde is an equivalence relation. What is an equivalence relation? It is a relation which is reflexive, symmetric, and transitive. To check reflexivity, we need to show that X tilde X for all X. But that's clear because you just take this as the identity group element. So x is of course e dot x because e dot x is x. So reflexivity follows. Symmetry. If x tilde x prime, then we want to show x prime tilde x. So we are given x tilde x prime. Therefore, there is some g such that x equals g dot x prime. And this implies that g inverse dot x equals x prime. And therefore, x prime equals g inverse dot x, just writing it in a different way. And therefore, x prime tilde x. So symmetry also follows and transitivity also follows. Just think about it. So this is an equivalence relation. And our lemma is that the equivalence class of x is same as the orbit of x. Okay. It's a very simple lemma. So which direction is the, I mean, both directions are easy, but let me see which direction to start with. Okay. So let's say E be the equivalence class of x. So first we will show that E is contained in x. So proof for E contained in orbit of x. Let x prime in E be arbitrary. Then there exists G such that x prime equals G dot x. Because if x prime is in the equivalence class of equivalence class of x, then x and x prime are related under the defined relation. And hence, by the definition of the relation, x prime is equal to g dot x for some g, which implies x prime belongs to the orbit of x. Now what we did was we picked an arbitrary element of the equivalence class and showed that it lies in the orbit of x, and hence this containment holds. For the reverse containment, let x prime be arbitrarily chosen in the orbit of x. Then by definition of the orbit, x prime equals g dot x for some g. Here also I should have written for some g, but I forgot about it. And this immediately implies x prime is related to x by definition, which implies x prime lies in the equivalence class of x. And that's it. That's the proof because we have shown both containments. Here we started with an arbitrary element of the orbit and ended up showing that it lies in the equivalence class. So that's the proof of this lemma. So we can capture the notion of orbits via this very natural equivalence relation on the set x. All right. Now, a consequence of the above is, suppose we are given an action on a set x and we have fixed an element of the set x. And for any element in the orbit of x, we have the orbit of that element is same as the orbit of x. We do not really need to use this lemma. One can just look at the definition of the orbit and prove it. But let us invoke this lemma and see why this holds. So by the above lemma, y is in the orbit of x is same as saying y is related to x. Since tilde is an equivalence relation, this is same as saying the equivalence class of y is equal to the equivalence class of x. But equivalence class of y, again by the above lemma, is the orbit of y, and the equivalence class is the orbit of x, and therefore this holds. So it's a consequence of the above thing. And another consequence of the above thing is that if g acts on x, then x is partitioned by the orbits. Equivalence classes partition any set. So if you have an equivalence relation on a set x, then the equivalence classes partition it. We just showed that the equivalence classes are precisely the orbits, right? And therefore, the set x is partitioned by the orbits. Again, we did not need to resort to all this language. We could have proven this directly using the definition of an orbit, but I think this is better. Okay. Transitive action. So fix an action of a group G on a set X. I've written it 2 times. Fix an action of a group G on a set X. We say that the action is transitive. Oops. We say that the action is transitive if there is only one orbit. Only one orbit. Okay. And note that an action is transitive if and only if the orbit of any element is everything. Is full. Let me write it that way. So what I'm trying to say is that if G is an action on a set, if G acts on a set X, then this action is transitive if and only if whatever element you choose in the set X, the orbit of X is the entire set X. And this is clear because first you assume that the action is transitive, then there is only one orbit, which means that every element is equivalent to every other element under the relation defined in the previous slide. And therefore, the orbit of every element is full. If the orbit of one element is full, then the orbit of every element is full. And you can do the other direction also. So just note this. And now let us look at examples. So this is a transitive action. We saw in the previous or maybe last to last slide that the orbit of any element is everything. It was sufficient to just check that for one element. If you see that the orbit of one given element is everything, then the orbit of any other given element is also everything. That is this remark. So we saw that this is a transitive action. This is not a transitive action. So recall, what is this action? This action is phi is a map from this to that, which takes t comma v to the image of v under t. So that is the map. That is the action. And this is not transitive simply because what is the orbit of the zero vector? The orbit of zero vector is only the singleton 0, because any linear map takes 0 to 0. Therefore, we have an element whose orbit is not everything. In fact, it's too poor. The orbit is too poor. And therefore, this is not a transitive action. But if you throw away the origin, so fix a field, it could be real, complex, rational, whatever, finite field, doesn't matter, then this guy acts transitively on that guy, meaning this action is transitive. So first of all, we need to actually see that this is indeed an action. And that is clear because a non-zero vector will go to a non-zero vector under an invertible linear map. So this big action, just replace R by F, restricts to this action. Okay, and this is transitive. The reason is very simple. It's just basic linear algebra. So one can show that you fix a non-zero vector. Let's say this. If this is your vector, call it V naught. Then we want to show that its orbit is everything. So let's say V is some other non-zero vector. We want to show that V is in the orbit of V naught. But the thing is, this can be extended to a basis. This is a non-zero vector, hence linearly independent. Any non-zero vector is linearly independent in a trivial way. Therefore, you can extend this to a basis. And now you can choose a linear map which takes the standard basis to that basis, element wise. So here this is one of the standard basis vectors. You pick all of them. Here you extend this to a basis in some arbitrary way and just map those vectors one by one, just the second vector maps to the second vector, third to the third. And that mapping gives you an invertible linear endomorphism, and that's it. So therefore there does exist some group element which takes this guy to that guy. So I have been a little bit sketchy here, but I'm sure if you know your linear algebra, this is clear. Okay. Now for the very important orbit stabilizer theorem. So again, fix an action of a group G on a set X and fix an arbitrary element in the set X. Then we define the stabilizer of X in the group G. So let me write that. This is the... okay, I will write that later. So what is this notation? This notation is all the elements of the group such that they fix X, they stabilize X. Right? If you hit them by the group element, they do not move. So collect all those group elements, and it is easy to check. Whoops. It is easy to check that this guy is a subgroup of the group G. So it is clearly closed under products. If you take G1 and G2 in the stabilizer, then we want to show the product G1, G2 is also in the stabilizer. So to do that, we need to find out what is this. But this is by the rules of the action. It's G1 dot G2 dot X. But since G2 is in the stabilizer, we have g2 dot x is x. So the above thing becomes g1 dot x, but g1 is also in the stabilizer, so this is equal to x. Therefore, g1 g2 dot x equals x, and hence this is also in the stabilizer. So this guy is closed under products, and similarly you can show it is closed under inverses, and therefore this holds. So we have a nice subgroup. Given an action, you can create such subgroups, and the theorem is, the orbit stabilizer theorem states that the index of the stabilizer is same as the cardinality of the orbit. This is nothing to do with finite groups and finite sets or anything. This is just the index of the stabilizer, meaning the cardinality of the set of all the left cosets of the stabilizer group, stabilizer subgroup, and this is just the cardinality of the orbit. So if if the group G were finite or the set X were finite, then this is actually an equality about numbers, but as such, this is a set theoretic fact. Okay, so let me also write that this is called the stabilizer. What color should I use? This is the stabilizer. Since there is only one group featuring here, sometimes we may drop this subscript, but I have retained it. Okay, so how do we prove that? So we will use set theoretic quotienting. So define a map from G to, let me write it in a different way. So define G to orbit of X. What is this map? This map takes little g to G dot X. That is our map F. Of course, this is not a group homomorphism or anything. That doesn't make any sense. This is a group. This is not necessarily a group. So there is no such thing. We're not talking about group homomorphisms here. This is just some map. Okay. And now let us try to find what are the fibers of F. So f of G1 equals f of G2 if and only if, give me a moment, if and only if G1 dot x equals G2 dot x, if and only if G2 inverse G1, let me not skip a step, dot G1 dot x equals G2 inverse dot G2 dot x, which happens if and only if by rules of action. Let me not put a dot there. This is equal to G2 inverse G2 dot x, which is G2 inverse G1 dot x equals x. Why? Because this is identity, and identity dot x is x. This happens if and only if the above statement is same as saying G2 inverse G1 is in the stabilizer of x, which is to say that G1 and G2 are in the same left cosets of the stabilizer, or we can write G1 times stabilizer of x is G2 times stabilizer of x. So F maps G1 and G2 to the same element if and only if they lie in the same left cosets of the stabilizer. Therefore, the fibers of F are precisely the left cosets of the stabilizer, right? And therefore, by set theoretic quotienting, this factors injectively through the set of all the left cosets of the stabilizer to give a map F bar. So this is an injective map. Also, the map F is clearly surjective. What we are doing is, what is the image of F? The image of F is all the elements of this form, but that is precisely the orbit of X. The map F is surjective, and since a surjective map always factors through to give a surjective map, the map F bar is also surjective. So we have a bijection between the set of all the left cosets of the stabilizer and the orbit of X, and therefore we have proven our orbit stabilizer theorem. So yeah, so this is called the orbit stabilizer theorem.